Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A big thanks to everyone who participated in, voted in, and supported our My AI contest. I'm excited to announce that our first place winner is, can I get a drum roll? Mohit Nalavadi. Mohit sent in the video Personal Healthcare Applications, which you can find along with the other entries at twimlai.com/myai. Second prize goes to Julian Ford for his entry, Dad and Eleanor. And third prize goes to Matt Taylor for his poetic and ominously named entry, Let Earth Not Become Our Tomb. Thank you all for entering, and stay tuned for our next contest. A special shout out to Lighthouse and Anki for donating the Lighthouse and Cosmo prizes. Check them out at lighthouse.ai and anki.com. In this episode, I'm joined by Raja Chatila, Director of Intelligent Systems and Robotics at Pierre and Marie Curie University in Paris, and Executive Committee Chair of the IEEE Global Initiative on Ethics of Intelligent and Autonomous Systems. Raja and I had a great chat about his research, which deals with robotic perception and discovery. We discussed the relationship between learning and discovery, particularly as it applies to robots and their environments, and the connection between robotic perception and action. We also dig into the concepts of affordances, abstract teachings, meta-reasoning, and self-awareness as they apply to intelligent systems. Finally, we touch on the issue of values and ethics of these systems. Before we jump into the interview, this is your final reminder that our next TWiML online meetup is tomorrow, Tuesday, March 13th at 5 p.m. US Pacific Time. This time, our focus will be on the Google DeepMind paper, Playing Atari with Deep Reinforcement Learning, in a presentation by Sean Devlin. Head on over to twimlai.com/meetup to learn more or register. Okay, let's get to it. All right, everyone, I am on the line with Raja Chatila. Raja is the Executive Committee Chair of the IEEE Global Initiative on Ethics of Autonomous and Intelligent Systems, as well as an IEEE Fellow. He's also a professor at Sorbonne University, Pierre and Marie Curie, and director of the Institute of Intelligent Systems and Robotics there. Raja, welcome to This Week in Machine Learning and AI.
Hello, everyone. Thanks for inviting me.
Absolutely. Why don't we get started by having you tell us a little bit about your background and how you got involved in intelligent systems, robotics, and ethics?
Well, let's see. I'll make a long story short because I've been working in robotics and artificial intelligence since a number of years now. Actually, I defended my PhD on mobile robot navigation in 1981. So That's quite long ago. And I've been working, therefore, in robotics and intelligent systems, intelligent robotics since that time, working on several aspects of those problems, including planning, action planning, motion planning, perception, decision-making, learning, and human-robot interaction. So it's a field that I've been familiar with since a long time, and which is evolving very, very fast, especially in the past few years, because the technologies that were developed over the years have come to some maturation, and we understand much better now a lot of processes and problems to be able to integrate them and get them to real-world solutions. And there have been also some progress, of course, which is enabling those technologies to become much more efficient, which is the increasing computer speed, availability of memory, of data, enormous amounts of data. So that fostered the whole field recently.
Great. And what's your current focus?
Well, currently I'm focusing on learning processes, how to get a robot to learn to interact with its environment. This is a basic issue, but the point is that we want the robot to learn through his or its perception, its physical interaction, to connect those two together without giving it much information a priori, so that it discovers actually what is its environment made of. We don't want to pre-program things. We don't want to supervise its learning process. We want this to be unsupervised, and we want the robot to connect its perception and action, because it's the only way, we think, to actually grasp an understanding of the environment. If you take perception in general, it's considered and developed as an observation process. You have images, and they process the images. You make some classification, and you come up with identifying objects in the scene. And this can be based, of course, on learning processes such as deep learning. But I think that this, of course, is very efficient and has proven efficiency lately. But by doing this, the robot doesn't really understand what it's looking at. To understand, it means that the robot has to develop a knowledge about what it can do, what it is its action scope, its action possibility on the objects in this environment. And therefore, it has to connect its perception with its action capacities. And this cannot be done separately. It has to be done simultaneously. So this learning process, which is based, of course, on processing data from sensors, but it's also based on reinforcement learning of interaction with this environment, would enable the system, the robot, to really connect its action capacities with its perceptual capacities. And this is what I call really understanding the environment.
Interesting. And now, is the robot learning all of this from the ground up, meaning you're firing up a system that has no a priori knowledge of its capabilities, and it's, exercising stepper motors and, figuring out what, degrees of freedom it has? Or what's the starting point for this understanding in your model?
Well, that's the main difficulty. Excellent question, I would say. What I want to do is to achieve this process with minimal initial information. Now, what is minimal? That's the point. It's not very clear. But if we define very basic and very specific minimal knowledge that the robot has when it's manufactured, I would say, or what is the initial programming that it has, and then starting from this, develop the whole process, but reducing more and more this basic knowledge. So, for example, if we start from really zero knowledge, just as you said, exercising the stepping motors, this will lead to a very big complexity, because there are many degrees of freedom, and there is a quite wide complexity also in the perception of the system. So we have to define a minimal set of processing capacities. For example, the system is able to determine verticals, horizontals, diagonals. It's able to identify some intersections. It's able to define some regions which have a common perceptual background. So these are minimal processing capacities that the systems come with, and in terms of actions, it is able to move its arm, for example. So we are not going to start with the basic stepping motor or basic motor, but a little bit more complex capacities that enable, for example, to move a whole arm to touch something.
Okay.
So starting from that, the development of the process can be made to understand how we connect perception and action together. Then we can get back to reduce maybe those initial assumptions, which are already small, but what we want to prove is the process itself.
You want to prove the process or improve?
Prove that it can work, that we can actually
Okay.
arrive to do this understanding. We want the system has to discover what is called affordances of the objects, of the elements of the environment that it's interacting with. And then we want to manipulate those affordances, which are those perceptual actual action representations, so that the system is able to extract more and more information about what it can do with them through this interaction.
And in order to prove or even measure the robot's understanding of its environment, you need some kind of representation for how, I guess, for these affordances. Like, how does the robot represent affordances, and how do you measure, I guess, the scope of the affordances that it has determined with an environment relative to the total number of affordances or space of affordances?
Okay, yeah, very good question. So the point is, some affordances are discovered initially because there are some initial simple interactions like pushing or holding or tapping. And this provides a first base, a representation, an affordance. It's not, of course, the complete representation. So then the process, which is based on reinforcement learning, tends to build more complex affordances. So this is guided, if I may say, through values. Values meaning that the system has a basic set of motivations that translate into rewards that it has when it discovers some representation that afford for those motivations, and reinforce, therefore, this kind of representation. But by repeating this process with those basic motivations, the idea is to build upon the basic affordances more complex ones. So let me give an example. When the robot pushes a given object, well, suppose this pushing will be actually pushing on a switch, and then there is light that
Okay.
as a result. And one of the motivation of the robot is to have a clearer environment. So then this object that it has pushed on, with which is the switch, is identified as affording light. But the initial representation was just a kind of box or a very simple object, which had other affordances. For example, the robot could be able to hold it or push it. But now it's associated with something new, which is light. And so it has a more, I would say, abstract property, which is not just its geometrical shape or the fact that it was pushable and so on. Now it's associated with light. And I can then use it for building up on more complex motivations, which, for example, are for fetching other objects, I need first to put on the light. And therefore, this object has become I don't really dare to pronounce the word symbolic, but that's what it is. It's not just described in its perceptual features, it's more described in some more abstract properties. It's related to this property of light, and the idea is that then we can build upon that again and again.
Yeah, I'm thinking a little bit of Josh Tenenbaum's work at MIT and trying to relate some of what you're doing to what I've heard of that work. And it's interesting in that I think what the way I think of what he's trying to do is like come up with this notion of common sense for like how things work. And what you're doing is starting from almost no common sense and trying to have the robot, figure everything out on the fly. I don't know if you're familiar with the stuff that he's doing, but I'm curious if you have any, if you could maybe help me contextualize how they might fit together.
Oh, yes, of course, I know about Josh Tenenbaum work. And work of many others in this area, which is not recent, of course. And there have been a lot of efforts and research to try to provide common sense to robots, to computer systems, and so on.
Right.
And so it's absolutely related. And I think the approach to building common sense should really be grounded in the physical interaction with the world. So this is how we build common sense, by trying to discover the effects of our actions. I'm speaking about the robot, of course. The effects of the actions
Right.
of the robot's action on the world. So without this knowledge, common sense would be just a very abstract representation. Wouldn't be really something that the robot is able to sense in its own actions. So it's of course in this general paradigm of developing common sense, and the approach is developmental. Again, similarly to what children do, they have some basic capacities, basic knowledge, basic sensing, basic action capacities. But when they start to experiment with the environment, this is where they discover that there is something called gravity. Of course, they don't call it like that, but they discover that when they hold something and they just let it go, it will drop to the ground. So
Right.
it means there is a specific effect from their action that is observed, and the connection between this perception and action is the major component of what is going to become common sense, which is this a description of the laws of physics, of what actually is the effect of actions on the environment. Then we will need something else, which is generalization, because what I'm speaking about is just the interaction of the system with its environment. But what happens when you observe other agents, for example, doing things, and how do you develop from that also representations that you can embed with your own actions. That's another step, which is, I think, also very important, but we are not doing this yet.
As opposed to having the robot learn from kind of base principles, everything about the world, shouldn't it have the benefit of the knowledge that we have? And for example, are there ways to, or should we move towards kind of ways of, representing the laws of physics, for example, and being able to provide that as an input model or something to the robot that it can kind of discover and use affordances with that knowledge, as opposed to needing to figure that all out from scratch?
If I can answer bluntly, I would say the more knowledge you input to the system, the less it will be able to understand its environment. It has to build, to some point, it has to build this knowledge by itself. Then it can maybe generalize or learn something that it can relate to its own experience. But I don't know if the following example is good. You can explain to me theoretically with the laws of physics how I can swim or how I can ride a bike. If I don't do it myself, I wouldn't really understand what you are talking about. Then if I do it myself and then I read or I learn the laws of physics about flotation, about the conservation of energy, of moments, and so on, well, then I can really theorize and understand what's going on when I ride the bike. So that's the idea. It's if we cannot anchor or ground on actual experience these notions, then we wouldn't really be able to understand these notions. So providing initial knowledge or information, especially if it's described in theoretical ways or ways that relate to how the humans actually understand this, I don't believe it will be much of help.
So one of the things that you mentioned earlier that I thought was interesting was that you put all of this, or the robot is exploring all of this in some set in a framework, a values-based framework, right? The robot has some values or motivation, and it strikes me that perhaps this is one of the hooks into the broader idea of ethics. Is that correct?
Aha, yes, well, values. Of course, it relates to some point to ethics, because the values I'm speaking about when you start to interact with the environment are more values that will, in the beginning, relate to what is able to answer the motivation of the robot. For example, just for the sake of simplicity, if the motivation of the robot is to have more power, to plug into a power device to have more energy, then this would lead the robot to search for those actions and those perceptual inputs that can lead it to better reach this goal, which is actually achieve this motivation. But then the idea is exactly to make those motivations more and more complex, starting with basic things like energy, for example. But then you can formulate motivations in a more complex way, because, for example, in order to reach the power plug, I might have to go to somewhere else because it's not located here. And therefore, as another motivation, there is the motivation to move, to have this motion to reach somewhere else where I can indeed be able to have my initial motivation fulfilled. So this is just an example to say that we can build more and more global or abstract motivations. I mean, that's my purpose, to the point that motivations can maybe lead to ethics in this case, because when I mention values, initially the values are those that are going to lead to some rewards. So
Right.
starting from basic rewards to more complex rewards, is it rewarding to have, for example, a positive interaction with another agent? How is it rewarding to have a interaction that is satisfying another agent's own motivations? Now, if you build on that, you can reach a point where this notion of motivation is going to, and the values behind it, is going to lead the robot to respect some maybe ethical values. Ethics is built, I mean, initially when the Greek philosophers, when Plato, Aristotle came up with the notion of ethics, the idea was to live the good life. The good life is what enables a society to hold together, what enables people to live in a society in which they have the ability to reach a form of happiness. That's what is the initial grounding of ethics. So how can we live together and live the good life? So it means that this comes from an ability to respect some values which make this social life possible, instead of each one trying to kill their neighbors. So this can be translated, although it's not what I'm doing now in terms of scientific research. This can be translated, if we want our robots to respect, to develop an ethical behavior or an ethical common sense. This can be also input as a motivation in the robot system. However, personally, I don't believe that, at least for some time, we can build robots that can grasp the meaning of some abstract notions, such as human dignity, for example. The notion of dignity, which also is very important in ethics. I don't believe that we can really define this, or I don't see a way for a robot, which is a machine, to discover what this means exactly. So there will be some border maybe that we will have to cross one day to try to achieve this. But today I don't see how we can really define or learn by a robot these abstract notions of human dignity, integrity, freedom, human rights.
I'm just curious. There are, abstractness is a spectrum. I'm not sure that it's a two-dimensional spectrum, but I'm wondering, do you have a sense for what's the most abstract thing we've been able to teach a robot, or any examples of things that are kind of towards the abstract side of the spectrum?
Not sure I can answer this. Well, it's
an abstract question.
Yes, no, because it's quite difficult to define what the robot has actually learned. When we say
Right,
what is the
right.
yeah, so what does the robot know exactly? Of course, I can program the robot to with some very abstract notions. And for example, speaking about emotions, I can program a robot that says "I love you," but I don't think the robot understands what love is. It's just the result of a specific programming, some parameters that have been input and that the system can measure and react according to those values of the values of those parameters. But understanding what love means exactly, I'm not sure. I'm even sure of the contrary that a robot can grasp this. So this is why I'm saying it depends what you mean by teaching and what you mean by understanding by a robot system of those abstract notions.
Yeah, I guess the things that came to mind were like I think we've been able to teach robots an abstract notion of shape, for example, that is, at a higher level than, point locations, and an abstract notion of relative position, like something being on top of another thing that again is like abstracted away from, stepper motor rotations and point locations and things like that. And it just occurred to me that there's a spectrum of abstractness. I don't know if it's those are pretty close to the physical side of on that spectrum, and maybe we're just kind of stuck around abstracting these base physical things, and I don't even know how to characterize the line between that and the next set of things. I was just curious if this was something that you've come across and thought of.
Yeah, I still believe that the examples you've provided, which are mostly geometrical examples, for example, or topological examples, something is above something else. I still believe that even if these sound as abstract notions that we have defined, I don't believe we have really made a robot understand what this means exactly. Of course, you can describe what it means, box A on top of box B or whatever, by defining some relationships between the shapes. But is this really defined in any situation? Is it that abstract? What will happen, for example, if you have a robot in outer space and there is no gravity? What does it mean, something on top of something else? I'm not sure a robot can grasp the profound notion of something on top of something else, because it doesn't even have this notion of gravity. And notion of up, down, and so on is very much related to our relationship with the world. So it's on top because I'm vertical, for example, and something is on top of something else because it's following this verticality, for example.
Right.
But when you change the referential, I'm not sure the robot can grasp what this means. So I believe our definitions are actually very much grounded in some knowledge that is not expressed, not explicit in the robot system.
So that kind of begs two questions for me. One is, what does understanding even mean, and what is the test for robot understanding? And secondarily, it also causes me to question this idea of having robots learn things from scratch. And in particular, if the robots are going to interact with and communicate with us as humans, and so many fundamental things about the way we perceive the world, like something being on top of it, is fundamentally connected to our humanness, in this case our verticality. Like, don't we have to give the robots a lot in order for them to develop an understanding of the world that even makes sense to us?
Yeah, well, that's exactly the point. I mean, if we want to build a robot that is useful, that we want to use tomorrow, that we want to use it for achieving tasks and with which we want to communicate and say, put this book on top of this desk, for example. Of course, we have to program things into those robots. But again, the robot is just a kind of zombie. It doesn't understand what it's doing. It's doing it, but it doesn't understand what it's doing. It's just repeating or executing some program that has embedded what is needed for it to do this task. If we truly, I mean, from a scientific point of view, not from an utilitarian point of view, if I may say, if we want really to understand what this means, what does it mean for a system, for a machine to develop those notions, well, then it's a different story. And this is what actually AI and robotics, in terms of scientific research, is trying to deal with. And we are still miles and years from understanding how we are going to do that. So, right. Two different things. And just to be a little bit more provocative, I would say my personal view is that to achieve this understanding, you said what understanding is, to achieve this notion of understanding, I believe something is necessary. It's the notion of self-awareness. If the machine does not have this notion, I don't believe it will be able to really understand, because understanding is related to me, I mean the self, being at the center, at the core of a process of interaction with the environment, and the capacity of reflecting on one's own capacities, one's own reasoning on what I'm doing, meta reasoning, if you wish. So I believe that if we are not able to develop these meta reasoning capacities, this self-evaluation capacity that enables to reflect on one's own place in the environment, in the universe, in the world, this notion of understanding would be just artificial, not genuine. And which leads us to this notion of are we able to build self-aware machines, conscious machines, self-aware machines? Right. That's another issue that is much discussed as well. But I think this is fundamental. Otherwise, we will always have systems that just act like zombies, not like entities that grasp what their environment and therefore what they are about, what they are doing, really.
Is there anything that you've come across in the research that is showing promising results at demonstrating some degree of self-awareness?
There are tons of publications on self-awareness, but frankly, I think we are just rotating around this notion like the planets are rotating around the sun, except that the sun we can see it, and consciousness or self-awareness we can't, and we don't have a clear definition of what it is. So this is actually the basic motivation between my work, is to try to understand if and how, and of course the question is still quite open, if and how we can develop this notion of self-awareness through the interaction of the system with its environment, the interaction of the system with other agents, other systems. The idea is that when you interact with the environment, you have to relate things to you. You have to recognize yourself in this environment. This is my action. This is my arm doing this. And this is therefore my volition, my will, my decision to act in this way. this my places the self in the center. This is related to, this means something to me because I can do something with it. If the system is not able to grasp this relationship between itself and its environment, it will not have self-awareness. So the self-awareness will be developed through this interaction with the environment.
It strikes me that some of the work that's happening in and around reinforcement learning, playing Atari games and the like, it strikes me that some of that is approaching self-awareness. The agent is clearly aware. Well, I guess we have to define aware, but there's a clear relationship between the actions of the agent and the environment, and the whole premise of the reinforcement learning environment is that the agent can manipulate this environment and maximize some objective.
Absolutely. The reinforcement learning, in my opinion, is a core to this. And this is a technique which is absolutely related to trying indeed to build, reinforce this understanding. The point is, of course, that in reinforcement learning, you have to learn the value function. It should be something that is discovered as well. And this means that I have to discover what is of value to me. And this gets us back to motivations. So there should be some minimal motivations upon which more complex motivations are going to be built, but there should be some minimal motivations. However, most systems doing reinforcement learning are focused on solving a specific problem. So you have systems with, of course, the concept is quite wide and quite general, but you have a system that's going to play Atari, as you said, or that's going to assemble boxes and so on with the same process. So again, the process is core, but the values and the way they translate into achieving the motivations of the system, that's a big point. So, for example, you achieve a system that is able to play, say, by reinforcement learning is going to play Go or to play Atari, whatever. But what about a system that says, I've had enough playing this game, let's do something else? Then it's going to actually reason differently. It's not just doing something that it has been designed to do. It's going to decide something else, to do something else, which maybe is related to a different motivation. That's a point in achieving a system that is not just doing what I have or learning to achieve what I programmed it to do. It has to be able from a wider set of motivations or a wider set of self-reflection capacities to jump, to initiate maybe other decisions that were not explicitly what I asked it to do at the moment. I'm not sure I'm clear, but the point is, if the system is not able to reflect on its own motivations and to change that, then it will remain prisoner in the compartment of actions and objectives that the programmer has completely defined. I'm not sure it's possible to get out of that compartment, but that's the issue. That's the point.
The notion of I guess we can call it self-agency that you just described, being able to come up with its own motivations. Do you think that's inseparable from the idea of self-awareness? Like, could a machine be both self-aware and yet unable to determine its own motivations?
Well, that's just a belief. I'm not sure. I think it's related, maybe to some degree. I'm not sure we can define. I mean, self-awareness is not necessarily something you have or you don't. You might have several degrees of self-awareness. There are some uh, studies about this in some for some animals, for example, for the maybe dolphins or for some apes, but so there might be some degrees of self-awareness. So I'm not sure there is only one degree, but eventually, yes, I think that this is related to this capacity of being able ultimately to have a kind of free will to
Right.
step out of the enclosure. So, and this might lead more explicitly to the notion of ethics, actually. Although we are trying to, in the IEEE initiative, to work on the ethical issues of today's autonomous systems, of today's intelligent systems, those which don't have those capacities, how do we reach a development or a design process of those systems so that they are compliant with human values. So this is a design methodology, for example. This is something that has to be considered and taken into account when people, researchers, engineers, designers develop such systems. But on the more research scientific side, of course, having an autonomous system or a system that is capable of reflecting on its own about ethical considerations. Well, that will be the ultimate thing. But as I mentioned earlier, I don't believe we are even close to that.
It is certainly a fascinating topic and one with many, many kind of interrelated layers. You know, we're coming up on the top of the hour. We've hit the top of the hour. I think we're going to have to schedule a part 2 at some point to go into the ethics of autonomous systems. There's a lot there to chat about as well. But I really enjoyed learning about your research and some of the ways you're approaching this idea of abstract thought and understanding for robotics.
Well, thank you. Yes, I'll be delighted to have another chat because indeed we just alluded very, very briefly to that, and but the conversation was very, very interesting.
Great. Well, thank you so much, Raja.
Thank you, Sam.
All right, everyone, that's our show for today. For more information on Raja or any of the topics covered in this episode, you'll find the show notes at twimlai.com/talk/118. If you have any questions for Raja, please post them there and we'll make sure to bring them to his attention. If you're new to the podcast and like what you hear, or you're a veteran listener and haven't already done so, head on over to your podcast app of choice and leave us your most gracious and glowing review. It helps new listeners find us, which helps us grow. Thanks in advance. And of course, thanks so much for listening, and catch you next time.